Hello, in this video we are going to look at complete beam design. A typical problem like this is worth 14 marks for you, a full question in the final exam. Now when it comes to beam design, the following steps have to be done. Let's read them. You have to find flexure or moment steel. You have to check development length. You have to check shear safety and then give reinforcement. You have to check for deflection, cracking, slenderness ratio. Then you have to draw a neat design sketch, and you have to also check practical requirement in the sense whether whatever detailing you have done and the concrete should have space to get between the bars. So let's look at these steps for a typical problem which you may get like this. Let's read it. It says a simply supported rectangular beam of 4 meter span carries a uniformly distributed characteristic load including self-weight of 20 kN per meter. The section of the beam is given 230 mm by 450 mm overall. Design the beam. The materials are given M20 and 415, and they have said the beam is suspended from the upper floor. Now please understand a few things. So this, as I said, this problem is worth 14 marks for you. So it's worth spending uh, time on each of the things. First of all, you understand characteristic load means working load, and you have to multiply that load by 1.5. Including self-weight means you don't have to again add the self-weight of the beam. And you see, when it comes to design, you have to actually decide B, D, and steel reinforcement. But normally what happens, B is either 230 or 250, and depth is either decided by architectural requirements or it is span upon depth. So that's why in this problem you are directly given to you 230 by 450. Another important thing here is the beam is suspended from the upper floor. Now this is useful for critical section of shear. If it is suspended from upper floor, then the shear for which you will design the beam will be at the support. If it was simply supported, then it would have been effective distance D from the support. At that point from shear force diagram, you have to work out shear force and design for this. Now let's start with the steps. First, let's work out mu maximum, how that is at the center of the beam. It will come to this 60 will come if you do WL square by 8 into 1.5, and Vu maximum will be WL by 2 into 1.5, and you have to take effective depth. So you have to assume some 16 mm bars. I assume that there could be variation, and effective depth. How does 412 come? 450 minus the cover 30 minus half of 16, that is 8 mm. That's what 412 comes. So you are all set. Now for moment steel, you find mu by bd square, get in your formula of PT, find PT which is percentage steel, and multiply PT 0.47 with 230 into 412, you will get the required steel. After you get the steel, you have to check if it is more than the minimum required and less than the balanced. Balanced, how you get for this? 2.76b. A balance, see, you have the AST balance will be, I think, for this combination 0.96. 0.96%. Okay, so from that you get 19. Now how to get AS minimum? AS minimum, so there is a formula which we did. Use this formula and find AS minimum. Now that you have provided AST is between AS minimum and AST balance, you are okay. If it was more than AST balance, then you will have to go for double. This problem is single reinforced only. Now 449, you choose number of bars. I have chosen 412, which gives 452, which is okay, slightly more than 459. It has to be always slightly more. Now next step is check for development length. There are two aspects. First, 12 dia bar, you need development length of 564. So look at this diagram. If you are going to curtail, then you have to curtail beyond 564, so that sufficient development length is given before curtailing. And another part of development length what you have to check is from this formula. mu1 by vu plus L0 should be greater than 47 times diameter of the bar, that is 12. Now you have to consider uh, it at the support. Okay, so out of 4, let's say 2 bars continue, so their area is 226. So corresponding PT is 0.238, and from there you you have mu1 by bd square. So from PT you get mu1 by bd square, and from that you work out mu1, vu is there, and L0 you always take as 100 mm. So you plug these numbers in the formula and you get 564, and then you see this you mu1 upon vu plus L0 you get 631, and 47 into you get 564, and as long as it is more than 564, your development length is checked. Next you go for shear. You have shear force, you find out tau v, and tau c you find out from that long formula. Since tau v is more than tau c, you are going to need shear reinforcement. So you find VUC, that is shear capacity of the beam. Find VUS, that is for which VUS is shear force for which you will design the shear reinforcement. So that is 28.54. And then for shear you have 4 things. You use SV formula, you use the minimum steel formula, 0.75D, and number 300. Minimum of these will be 132. So you are providing 6 at 130 towards the support, and then at 6 at 300 you will adopt at the center for the simple reason that in the central portion shear force is less than half of the shear capacity. So this is your complete design. Rest is simple. Check for deflection. All you have to show is for your beam span to depth ratio is actually less than 20 is good enough. 24 we have used modification factor, but even if 9.71 is surely less than 20, so it's okay. Check for cracking. All you have to do is between the two reinforcement bars, main bars, 12 bars, you make sure that the distance is less than 180, which is so if you do the detailing. And for slab this is the criteria, but this is not applicable here. Now here in our detailing, beam distance will come to, the distance between the two main bars will come to 40.66, which is less than 180, so you are okay. Then slenderness ratio. See, for simply supported beams, clear span should not be greater than 60B, which is so here, and also it should not be greater than 250 B square by D. So both are satisfied, so you have shown the slenderness ratio. Now practical requirement is, see, the distance between two bars is 40.66, right? So and actual requirement is 25 mm, okay, or at least 12 mm. See, no, this is aggregate plus 5 mm. Okay, so aggregate plus 5 mm. So I would say roughly the distance between two bars must be more than 25 mm, because then only concrete will. Then this is very important. See, every problem will not be complete unless you draw the design sketch. Now one thing, this design sketch I have drawn for simply supported beam. Since it is hanging, this supports you have to sew up. Now everything in this has to be drawn. I'll just mention section AA is at the center, section BB is at the end. Why it is there? Because in central section there will be more bars. Here there are 4. At the end only 2 bars will continue. You have to give B and D. Stirrup spacing will be different in section A and B. Then you remember this for development length distance you have to mention. You have to mention where it is curtailed. You have to show the span. And this has to be as neat, because I must say That examiner first looks at the sketch and then he looks at your other whatever you have written. So it's worth 40 marks. Practice this very well. Thank you.